Welcome to my channel Learning Electronic Circuits. Here you can learn more about different electronic circuits, its working principles and the construction techniques. Resistors in series and parallel. In circuits, resistors can be connected together in series connection, parallel connection or a combination of both to form a more complex resistor network. The resistor network has a resistive value which is equal to the combination of individual resistors. There are three important types of resistive circuits: the series resistive circuit, parallel resistive circuit, and the series parallel resistive circuit. Whether the circuit is a series combination network, parallel combination network, or a series parallel combination network, they obey the rules of Ohm's law. In these resistor networks, we can measure their voltage, current, and resistance values. Resistors in series. Here the resistors are connected together in series, which is connected one after the other by their leads. The same current passes through all the resistors one by one, as there is no other way for the current to pass through. The series connected resistors have a common current that flow through all the resistors equally. Here the current IR1 equal to IR2 equal to IR3 equal to IRN, or any number of resistor current values. This method is used to calculate the total resistance of any number of resistors connected together as a series network. When the resistors are connected in series, the total resistance of the circuit is calculated as RT, or total resistance, equal to R1 plus R2 plus R3 plus Rn, or any number of resistor values. The voltage across the resistor network is calculated as Vs, or source voltage, equal to VR1 plus VR2 plus VR3 plus Vrn, or voltage across any number of resistors. Here the voltage varies across all the resistors. The current across the resistor network is calculated as IT, or total current, equal to Vs by RT, or source voltage by total resistance, equal to VR1 by R1 equal to VR2 by R2 equal to VR3 by R3 equal to Vrn by Rn. Here the current is the same across all the resistors. Voltage divider network. A voltage divider network is used in circuits to obtain a specific voltage for various purposes. Voltage divider networks are used in biasing of the transistor, regulating the voltage points in ICs, impedance matching networks, etc. The calculations in a voltage divider resistor network is as follows. Total resistance RT equal to R1 plus R2. Total source voltage Vs equal to VR1 plus VR2. Vout equal to Vs R1 by RT equal to Vs R2 by R1. Resistors in parallel. Here the resistors are connected in parallel. Both the terminals of the resistor are connected to each of the terminals of the other resistor. The current in a parallel resistor network flows through different paths. The current that flows through each resistor is not the same, but the voltage drop across the resistor is the same. All resistors have the same voltage across their terminals, but have different current values. This method is used to calculate the total resistance of any number of resistors connected together in a parallel network. When the resistors are connected in parallel, the total resistance is calculated as 1 by RT, or total resistance, equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by Rn, or any number of resistors. The total voltage across the resistor network is Vs, or source voltage, equal to IR1 equal to IR2 equal to IR3 equal to IRN, or any number of resistor voltage values. Here the voltage is the same across all the resistors. The total current across all the resistors is calculated as IT, or total current, equal to VR1 by R1 plus VR2 by R2 plus VR3 by R3 plus Vrn by Rn, or any number of resistor current values. Here the current values varies across all the resistors. Two resistors in parallel. This method is used to calculate when two resistors are in parallel. When two resistors are connected in parallel, then the total resistance is calculated as RT equal to R1 into R2 by R1 plus R2. Series parallel circuit. Here the resistors are connected together both as a series circuit as well as a parallel circuit. Some of the resistors are connected in series, whereas others are connected in parallel in the circuit. It may be a complex network of interconnected circuits. The current passes through both the series and parallel circuits when the voltage is given. The total resistance of a series parallel circuit or a more complex circuit is calculated using the series circuit's formula and the parallel circuit's formula. The circuit is broken down into simpler series or parallel circuits. Calculate the total resistance of all the parallel circuits first. If there are series circuits within the parallel network, determine the total resistance of those series circuits first, calculating the resistance from the inner circuit and then moving outwards. When the equivalent resistance of the inner circuit is found out, redraw the circuit. Then calculate the resistance of the remaining part of the circuit moving outwards. Hello once again to my channel Learning Electronic Circuits. Today I am going to demonstrate about resistors that is connected both series and parallel. We have got here some resistors. These are all 1K resistors. I also have some 100 ohm resistors here, and this is a battery. We have an just for visualizing. This is a LED that is connected to a wire. Now let us measure the value, the ohmic value. These are all 1K resistors. I've turned the multimeter range to 2 kilo ohm resistor range. And here I got the resistor that is connected between the terminals, and here it shows 0.983. It's almost like 1K kilo ohm resistor. It's near to 1 kilo ohm resistor. There is a slight variation, maybe due to the tolerance of the resistor. It's just an LED disconnected. And let us now just connect. These are all 1K resistors. Let us connect these resistors in series. Let us now connect this in series. I'm just going to connect this in a series method of connection. So now these three resistors are connected in series. And, we have the battery that is connected to external wire. So it's a wire, and we just let us now check the voltage. That is, so now let's position this to the DC voltage range. That is 20 volt range, DC volt. And one of the negative terminal of the battery that is connected to the multimeter. Here we got the multimeter, negative terminal of the multimeter, negative probe of the multimeter. Then we have the positive terminal that is connected to the resistor that is connected in series. Here we get the voltage range, that is 9.41 volt. Yes, and the voltage source value is 9.41 volt, and we will connect this to the other end of the resistor, first resistor, and we get the value 9.40. Then we will just change the connection to the other terminal of the second resistor, and we get the value of 9.39 volt. And just change the connection to the next terminal, we get the value 9.38 volt. So likewise, maybe we can connect any number of resistors. We can connect any number of resistors in series. These are all resistors that are connected in series. These are all same value resistor. These are all similar value of resistor. So we now have 1, 2, 3, 4, 5 resistors that is connected in series. So we can check each the voltage in each terminal of the resistor. Here you can see that you get the voltage 9.40. Then here we get the value 9.39. Here we get the value 9.38. At the other end of this network we get the value as 9.35. So this is how we can reduce the voltage. This we call this as voltage dropping. In case we need to have a reduced voltage that is needed for a supply, we can reduce the voltage through this method. We can connect this in series, or maybe you can use a higher value resistor here. You can increase the value of the resistor here. So this is one of the uses of connecting resistors in series, just to drop the voltage, to getting a dropped voltage for a circuit. Just measure. We also have the current that is passing through these resistors. So the total current will be the same for all the resistors. The current that passes through the resistor is the same, but the voltage at the terminals of individual resistors, that remains altered. Let us now place the knob in the 200 milliampere range, and we got this series resistor here, and we are connected one end of the LED. This is the LED. You can see the LED here. I am connecting it to this place. You can see the LED's light is glowing up. And you can also change the position, and you can also see the current that is measured. The current value that is measured 1.4 milliamp. Here at the end you can see the 1.1 milliamp. Here you can see 1.3 milliamp. You can see 1.7 milliamp, and here you can see 2.3 milliamp. This you can see 3.6 milliamp. So when you here you can also see that it's 7.1 milliamp current. So when you raise the value, when you connect the value near to the voltage source, it draws more current. It draws more current, and it takes more current, and it shows it through the multimeter. Now you can see the total current that is passing through the series of 5 resistors. That is it's like somewhere near 1.4 milliamperes of current. And we just disconnect this terminal here, and I will connect it directly to the end of the other terminal of the and we'll just untie this one, disconnect this resistor, and just check the value, that is check the current that is passing through this resistor. You can see it's almost it's similar as 1.4. This reading is similar as 1.4. We just will just connect this together. We'll connect these two resistors together, and we'll check the amperage. Here also you can see it's 1.4. We'll just tie this to this connect. We'll just connect this together again. And we'll untie this and disconnect this resistor, and we'll check. Here also you can see the amperage, the current value, the current that is flowing through this resistor network. It is almost the same. The current is the same, but the voltage across the resistors are different. So here also you can see the current value that is it's the same. Just connect this one. And we'll just disconnect this and test. Here also you can see that the resistor amperage, the current value that is the same. That is the same 1.4 milliamperes of current that is passing through the series resistors. So the current across any resistor that is connected in series is the same, but voltage across the resistance differ. Now we have connected all dissimilar resistors here. This is a 1.5 kilo ohm resistor. Then we have the 3.9 kilo ohm resistor. Then we have the 100 ohm resistor, then 2.2 kilo ohm resistor, then 220 ohm resistor, and the 1k resistor. These are all connected in series. We have altogether 6 resistors in series. So we'll just check the voltage level for each of these resistors. I'm just connecting the multimeter, one of the negative probe of the multimeter, to the ground, to the negative pole of the battery. Here, just connecting the negative probe of the multimeter with the negative end of the negative side of the battery, and we'll just check the voltage level at each resistor points. Before that, we'll turn this multimeter position to 20 volt range. So we'll place it in the 20 volt range, and we'll just check the voltage. And here we get the voltage 9.25 volt. This is the voltage here at the end point. Then we have at the next position we get 9.26 9.26. When we place it in another position, it's almost 9.26, similar range. It's almost similar measurement. Here 9.28. Here we get 9.29. Now the voltage is getting increased, after 9.29, and here we get the voltage 9.32, and at the terminal point at the 9.33 volt. So we get a very varied voltage across the terminals in series connected resistors. We get an array of voltages, a different range of voltages. Network. This is a series connected network. This is resistors that are connected in series. These are all different values. The resistors are all different values. This is a 1 kilo ohm resistor. This is a 3.9 kilo ohm resistor. So 100 ohm resistor. There is a 1.5 kilo ohm resistor. There is a 220 kilo ohm 220 kilo ohm resistor and a 220 ohm resistor. So these are all different value resistors. We are connecting it in series. So let us now check the resistor, the value for this, the total resistor value, the effective resistor value, and I will just connect the resistance one end of the resistor terminal and the other end, and we can see that it's showing around 8.88 kilo ohm. So that is the effective resistor value here. 8.88, that is the effective value of the series resistor network. We have some dissimilar resistors. This is a 1 kilo ohm resistor, and this is a 220 ohm resistor. This is 3.9 kilo ohm resistor. This is 100 ohm resistor. This is 1.5 kilo ohm resistor, and this is 2.2 kilo ohm resistor. These are all dissimilar resistors in parallel. So now we are going to connect these resistors in parallel. So here, just tie it up like on a piece of copper wire. It's an open wire. This is just connect each resistor to that. So we just connect these resistors like this, and just connect this all resistors in parallel like this. And just connected all these resistors in parallel. Here we have another wire, that is this is another copper wire. We just tie this the other ends of the resistor, this copper wire. And like this we'll tie it up. We'll connect these resistors. We have seen all these resistors. These are all resistors that is connected in parallel. We have completed a parallel resistance. We made a parallel network, resistance network. Adjust the multimeter range to 200 ohm, and we'll just check the resistance. You can see it's somewhere around 58 ohm. So across the terminals of all the resistors we get an equal voltage, that is 6 point around 7 volt that you are getting across all the resistors. But we'll have to check each resistor separately for getting current values.